The question that I have is, how do you analyze data from a direct shear test? Some details of the direct shear test are shown in this picture. The test is conducted in what is called a direct shear box. The box has two halves, the top half and the bottom half. You can slide one relative to the other in the horizontal direction. So what you do is you fill this with soil, apply a normal force N1, and then pull the top half relative to the bottom half in the horizontal direction. So when you do, you're forcing the soil to fail along a horizontal plane like shown here. If I take a little differential element around the failure plane and draw the stresses on that plane, you get something like this. So this horizontal plane represents the failure plane. This is the vertical plane. We of course know the shear stress on that because the shear stresses are the complementary shear stresses, right? But we don't know the normal stress on that plane yet. So here's the Morse circle representing the stator stresses in this element, and this point represents the failure plane. You might wonder why I plotted this point in the negative direction. Well, I used our earlier sign convention, which is counterclockwise shear is positive, clockwise shear is negative, right? So on this plane, I have a clockwise shear, and therefore the point plots in the negative tau direction. Well, the failure plane has to lie on the failure line, and I'm only considering a cohesionless soil at this point, and therefore the cohesion is 0. The failure line has to pass through 0, right? The slope of this line is phi. So just by knowing the shear stress and the normal stress at failure, we can evaluate the friction angle of the soil from this test. I'd like to make some important notes here. Number one, the principal stresses and principal planes are rotating continuously during the test starting from the beginning. In the beginning, we put the soil in here and apply the vertical stress, right? So then this and this are the principal planes. There are no shear stresses because we haven't started applying the shear force yet, right? But then as soon as you pull it in the horizontal direction, pull the top half in the horizontal direction, you are applying a shear stress on the horizontal plane, and therefore the horizontal and the vertical planes are no longer the principal plane. At failure, these are the principal planes. So we can actually, using the principles of the Morse circle, we can evaluate the direction with respect to this horizontal plane. Why is this a big deal? Well, soil is inherently an anisotropic material. When you have something like that, we like to have a control on the direction of principal loading. If we have a control, then we can find the shear strength in the horizontal and the vertical directions of this anisotropic soil. But if the principal loading is rotating during the test, then of course it's rotating with respect to the initial direction of the principal anisotropy. So you don't know whether you're actually getting the vertical shear strength or the horizontal shear strength. But this is not a huge deal from a practical point of view. But if you do want to get a handle on anisotropy, then direct shear test may not be the most suitable test to do. Sometimes you want to know what happened to the stresses in the vertical plane, right? Well, the vertical plane and the horizontal plane are 90 degrees apart in the actual picture, therefore they have to be diametrically opposite on the Morse circle, right? And therefore this is the vertical plane. So if I give you some numbers for this, then obviously we can evaluate the normal stress and the shear stress on the vertical plane. Let's do a numerical example. These are the values of the stresses at failure, and we are interested in finding the friction angle, sigma 2f, which is the normal stress on the vertical plane, major principal stress, minor principal stress, and the directions of the principal planes. Finding the friction angle is pretty easy. All we have to do is to consider this triangle right here. This distance is 150, right? That's the shear stress. This distance is 100. That's the normal stress. this divided by that equals tan phi, and that gives us a friction angle of 56.3 degrees, which is a little high. So let's think of this as a theoretical exercise. Finding the value of sigma 2f is not too difficult either, it's just geometry. So what I did was I considered this triangle and found the radius first. So radius works out to be 270.4. Then by considering the same triangle, I found this distance AB, which works out to be 225. We know the AB and BC are equal to each other, right? Alright, so first I found the distance to the center, O to B, by adding AB to OA. So 100 plus 225, that works out to be 325. So now we know the distance to the center. All I have to do is to add BC to it in order to get the value of sigma 2f. So that works out to be 550. We take the distance to the center and add a radius to it in order to find sigma major, and that is calculated to be 595.4. And then we take the distance to the center, subtract the radius in order to get sigma minor. So that works out to be 54.6. So to find the direction of the minor principal plane, I take this radius and rotate it clockwise through this angle, which is 90 minus phi, right? So that's 33.7 degrees. And I get to this point, which represents the minor principal plane. So in the real picture, what I need to do is to rotate this horizontal plane in the clockwise direction through an angle of about 17 degrees, and I get the minor principal plane. So this is my minor principal plane. Once I know the direction of the minor principal plane, I can easily locate the direction of the major principal plane. Why? Because we know the minor and the major principal planes are perpendicular to each other. So this is my major principal plane, and that is where the major principal stress of 595.4 is acting.